Welcome to the fourth lecture of PH 4105, Advanced Mathematical Physics, a course on differential geometry and algebraic topology. In the past couple of lectures, we have looked at the notion of charts on a set. Let me remind you that a chart U phi is an ordered pair on a set M if the following holds. U is a subset of M. Phi is a map which carries U onto Rn, and it is a one-to-one map onto phi of U, which happens to be an open set of Rn. Since phi is one-to-one, if you were to restrict its range to phi of U, that is, think of it as a map from U to phi of U, it becomes an invertible map. An inverse map, phi inverse, carries the point of phi of U back to the set M, in particular back to the point in the subset U of the set M. So what phi does is that for each point in U, it associates a set of n real numbers, the numbers being the components of phi of P, and conversely, given a set of n real numbers inside phi of U, phi inverse associates a unique point which is in U. Now, the reason why a chart is at all useful is that it helps us to make a piece of an arbitrary set look like Rn, and in particular, it allows us to be able to differentiate functions on the set M. The function f from M to R will be called differentiable at a point P in U if the following holds. If you compose phi inverse followed by f, that is, a map which takes U from a point in phi of U first via phi inverse to the point P in U, and then via f to R, that is, the composition of course takes you from phi of U to R. If this function is differentiable at phi of P, you say f is differentiable at P. In fact, if the function f composite phi inverse, which we will call the proxy function, is differentiable of class Ck at phi of P, then f is differentiable of class Ck at P. That's the definition. Now, one thing which complicates matters here is that one single chart may not be able to cover all of M. And so, in order to talk about the differentiability of a function f defined all over M, you may have to switch charts in between. Now, this can lead to a problem. After all, it is possible that a function which is differentiable according to one chart is not differentiable according to the other. And of course, this will become a problem when the domains of two charts overlap, so that you could use either of the two charts to talk about the differentiability of a function at a point which is inside the overlap. In order to prevent such disastrous things from happening, you must make an additional demand. And the demand is that we need these charts to be compatible. And once you have established that all the charts you are using are compatible and together their domains cover the entire set M, what you have managed to create is a differential structure, a structure which will allow you to do calculus on M, and given this structure, the set M becomes what is called a differentiable manifold, the thing that we are all seeking. Let me now talk about what exactly does compatibility of two charts mean in some detail. But first, let me remind you of a definition from the calculus of many variables, a definition that we are going to need soon. If A and B are two open subsets of Rm and Rn respectively, then a function f from A to B is said to be of class Ck if all its kth order partial derivatives exist and are continuous. So in order that a function be Ck is not sufficient that all its kth order derivatives merely exist. These kth order derivatives should be continuous. We will soon be talking about C infinity functions only, functions which are differentiable arbitrarily many times. But for the time being, let us focus on what would happen if we were dealing with functions which are differentiable only k times and not necessarily more than k times. Now, with this definition under our belt, let us talk about the compatibility of charts on a manifold. Now, for this, what we need to talk about is the situation where you have two charts u, phi and v, chi on a manifold M. Now, these two charts u, phi and v, chi are called Ck compatible or Ck related if either the domains u and v are disjoint, in which case they are trivially Ck compatible, or if the domains are not disjoint, then u intersection v, of course, is a non-empty set, and the result of mapping that non-empty set using the chart map phi or the other chart map chi both lead to open sets of Rn. Of course, we are assuming here that the manifold M is n-dimensional. But that's not all. You need phi of u intersection v and chi of u intersection v to be open subsets of Rn simply so that the next very important part of the definition can at all be talked about. Now, phi composite chi inverse is a map which cannot be defined over all of chi of v. Of course, if you took any point in chi of v and applied chi inverse to that, that will give you a genuine point on the manifold M. However, that point might very well lie outside the domain u of the first chart, and so phi may not be applicable to that particular point. So phi composite chi inverse can only be applied to points which you get when you apply chi on u intersection v. So that when you apply chi inverse on a point here, you end up with a point in the manifold which is in both u and v, and since that point is in u, you can also apply the map phi to it. And this, of course, gives the resulting point which will be in phi of u intersection v. So this phi composite chi inverse is the map from chi u intersection v to phi u intersection v. Now this is one of the two transition functions we are going to talk about between these two particular charts. The other one, rather obviously, is the one which goes the other way around. It's chi composite phi inverse. You apply phi inverse first on a point which you get when you apply phi on something in u intersection v. So that phi inverse applied there takes you back to u intersection v. Then you apply chi on it to get a point in chi of u intersection v. So these two particular functions are going to take center stage in our definition of compatibility, unless of course u and v are disjoint sets. Now the demand that we make for the two charts to be Ck compatible is the following. You demand that phi composite chi inverse and chi composite phi inverse are both differentiable functions of class Ck. Remember, in order to talk about differentiability of a function defined on a subset of Rn, that particular subset of Rn has to be open. And that is why we demanded that both phi of u intersection v, which is the domain of the function chi composite phi inverse, and chi of u intersection v, which is the domain of phi composite chi inverse, are both open subsets of Rn. Note that these two functions, phi composite chi inverse and chi composite phi inverse, map a bunch of n real numbers to another bunch of n real numbers. So the ordinary notions of differentiability on Rn apply to these functions. And all we are saying is that these two transition functions will have to be of class Ck, and only when that happens are we going to say that these two chars are Ck compatible. Now, a picture should make the concept behind such a definition clearer. Unfortunately, the picture that I managed to draw has ended up becoming rather cumbersome, but let me try to explain what I am trying to show here by going slowly over pieces. Our manifold M is this region which I have denoted by this orange boundary. M is basically denoted by points inside this orange boundary. Now our two chars u phi and v chi have domains u and v which are subsets of M. U is the region inside the magenta curve here, and v is the region inside this light blue curve here. And the intersection of these two regions have been shown here, shaded with these dotted green points. So that's the u intersection v. And we are focusing our attention at a point P, which is inside this u intersection v region, so that I can use both the chars u, phi and v, chi when we are talking about putting coordinates on point P. So the chart u, phi uses a map phi which maps P to this particular point phi of P, whereas applying chi on P moves you to this particular point chi of P. I have deliberately drawn the two copies of Rn separately. They are both actually Rn's, but I have just drawn them separately in order to keep the things somewhat less cluttered than it already is. Now in this picture I have also shown this region of Rn, this subset of Rn, which you get when you apply phi on all of u. So this is phi of u, and here you have chi of u. Chi of v, actually, this should be v. Now, the region which has been colored green here is what you get when you apply phi on u intersection v. So this is phi of u intersection v. Similarly, here you have chi of u intersection v. Since our point P is in u intersection v, phi of P is inside phi intersection v here, phi u intersection v here, and chi of P is inside chi of u intersection v here. Now let us take a look at our transition functions. Let's focus on phi composite chi inverse first. This function acts on this chi of u intersection v. This region shaded blue here. In particular, it can work on this point chi of P, which is inside the region. When chi inverse acts on this, as shown by this dotted line, it goes and takes the point chi of P back to P. Then phi acts on this to produce the point phi of P. So in particular, if you applied phi composite chi inverse on chi of P, your result would be phi of P. So this gives rise to a map which takes chi of P effectively all the way to this point. This map is what I have denoted here by this dashed black line. So phi composite chi inverse, phi acting after chi inverse, takes you from here to here. Of course, this map acts on all points inside this region shaded blue to give points in this region shaded green. So chi of u intersection v gets mapped onto phi of u intersection v under the action of this particular map. What about the other transition function, chi composite phi inverse? So now let's focus on points in phi of u intersection v, and again in particular on the particular point phi of p. Phi inverse acting first will take you back to the point P, and then chi, this solid blue line, will take you to chi of P. So, Just like phi composite chi inverse took you from chi of p to phi of p, chi composite phi inverse does just the opposite. It takes you from phi of p to chi of p. This of course indicates that these two functions are inverses of each other. And what you have here is this function which we have denoted by the solid black line, chi composite phi inverse, takes you from a point in this region shaded green to the region shaded blue. Now, the compatibility condition that we demand here is simply that both of these functions, phi composite chi inverse and chi composite phi inverse, be differentiable up to k times and their kth partial derivatives be continuous. That is, they be functions of class Ck. That is what it means when you say that the two charts u, phi and v, chi are Ck compatible. Now, what exactly is the reason why we make such a demand? Recall that a function f from M to R is said to be differentiable at a point P belonging to the domain U of the chart u, phi if the proxy function f composite phi inverse, which maps this open subset phi u of Rn ultimately to R, is a differentiable function at the point phi of P. Now, this definition can of course be used for multiple differentiations. So, the function f from M to R is said to be differentiable of class CR. F is CR if f composite phi inverse is a CR function. That is, has rth order partial derivatives which are all continuous. Now, the whole question that we want to address is, if the point P belongs to the intersection of two different domains u and v of two different charts, and we use the proxy functions f composite phi inverse or f composite chi inverse to talk about its differentiability, are we going to get the same result or not? And the answer is provided by the following. If f from M to R is differentiable of class CR under the chart u, phi, it is also of class CR under a Ck compatible chart v, chi as long as R is less than or equal to k, and vice versa. It works also the other way around. That is, if f is differentiable of class CR under chart v, chi, it is also CR under chart u, phi. And the reason behind that is simple. F composite phi inverse, this proxy function according to the chart u, phi, is actually a composite of f composite chi inverse, the proxy function according to the chart v, chi, with the transition function chi composite phi inverse. Similarly, the other proxy function f composite chi inverse can be obtained by composing f composite phi inverse with phi composite chi inverse. So, of course, you apply phi composite chi inverse first, and then you apply f composite phi inverse. Because composition of maps is associative, it's easy to see that you can change the brackets here to talk about phi inverse composite phi, which will give you the identity, and therefore you will end up with f composite chi inverse here, and a similar argument can be given for this. Now notice that if f composite chi inverse is CR, then it's differentiable R times, chi composite phi inverse is differentiable K times, and it's a standard result in calculus on Rn that if you compose two functions, one of which is differentiable up to R times and the other which is differentiable up to K times, the resulting function is differentiable up to R times, provided of course R is less than or equal to K. And that is exactly what this statement is telling us. And that is really the reason why we demanded the transition functions are differentiable up to class Ck If they are differentiable up to class Ck, then you can talk about differentiability of a function up to any order less than or equal to k without worrying about whether which chart you use is going to affect your result. Whichever chart you use, you will get the same result. Of course, you have to remember that if you have a Ck compatible pair of charts, then talking about differentiability of order which is larger than k does not make absolute sense. A function may be differentiable up to L times, where L is greater than k, according to one chart, and fail to be differentiable L times according to the other. So let me emphasize once again. If you have a pair of Ck compatible charts, then the most you can talk about is differentiability up to order k. Let us now take a look at a few examples of Ck compatible charts. In fact, we will begin with the two examples where we have seen that a single chart fails to cover the entire set involved, and we have found out two charts which do. The first example is simply that of Sn, the n-dimensional sphere. In the last lecture, we had found out two distinct charts on Sn whose domains together cover the entire sphere. These were the stereographic projections from the North Pole and the South Pole respectively. The first of these, the stereographic projection from the North Pole, has as its domain U the sphere Sn with the North Pole taken out, and the corresponding map could be described geometrically, something which we have done in some detail in the last lecture. The upshot of all this is the bunch of coordinates which Sn has, a1, a2 up to an plus 1, are coordinates of a point on Sn whose squares add up to 1. These coordinates map to a bunch of n numbers which are basically a1, a2 up to an, but each one of them divided by 1 minus an plus 1. Note that this is a perfectly legitimate thing to do because the North Pole is the only point for which an plus 1 is 1, and since that has been taken out from Sn, when you constructed the domain U, the denominator of these divisions, 1 minus an plus 1, is never 0. We had also worked out that the inverse map takes a bunch of n numbers b1, b2, bn, the so-called coordinates of the point, and returns a point on the sphere whose coordinates in the embedding n plus 1 dimensional space is given by this formula. Basically, the first n coordinates are twice bi divided by sum of all the bi squares plus 1. The last coordinate, an plus 1, is given by minus 1 plus the sum of all the bi squares divided by plus 1 plus the sum of all the bi squares. So this was one of the charts. The other one, the stereographic projection from the South Pole, V, chi, has a very similar structure. The domain V is Sn with the South Pole removed, and the chart chi takes a1, a2 up to an plus 1. These, remember, the coordinates of a point on the sphere in the embedding n plus 1 dimensional space, and these map under the projection to a bunch of numbers a1, a2 up to an, each divided by the number 1 plus an plus 1. Once again, the South Pole having been removed from the sphere, an plus 1 is never minus 1, and so the division is perfectly legitimate. And chi inverse, the inverse map, takes a bunch of numbers c1, c2, c3 up to cn to this final set where all the ci's are doubled and divided by 1 plus sum of all the ci squares to form the first n coordinates. The last one is given by 1 minus sigma ci square by 1 plus sigma ci square. So these are the charts that we had already found out. Now what about their compatibility? Firstly, we have to look at the intersection of the two domains U intersection V where the question of compatibility actually plays out. It's very easy to see that in this case the intersection happens to be the entire sphere from which 2 points, the north and the south poles, have been removed. And what about the effect of mapping this U intersection V via the two maps, phi and chi? Remember, the images of U intersection V under phi and under chi have to be open sets of Rn for this to work. It's easy to see that whereas phi would have mapped the entire set U to the plane Rn, U intersection V gets mapped onto the entire plane Rn from which one point is removed, which is nothing but the image of the south pole, which is the only point of U which U intersection V does not have. The image of the south pole under pseudographic projection from the north pole is nothing but the origin. So phi of U intersection V is Rn from which the origin is removed. It's easy to see that such a set is an open set in Rn. And it's equally easy to see that if you apply chi, the pseudographic projection from the south pole map, on U intersection V, you get back the same image, that is Rn with the origin removed. So both phi U intersection V and chi U intersection V, which in this case happen to be the same set, are open sets in Rn as we are demanded. The next step, of course, involves looking at the transition functions phi composite chi inverse and chi composite phi inverse. Let us first deal with the transition function phi composite chi inverse. This takes chi of U intersection V, which is Rn with the origin removed, to phi of U intersection V, which of course is the same set once again. Now let's do this in steps. First, chi inverse acts on a point of chi of U intersection V. There is a point in Rn with coordinates C1, C2 up to Cn, let's say. And of course, the only restriction here is that all the Ci's cannot be 0. Now, the action of chi inverse on this has already been described a while ago. All the Ci's gets multiplied by 2 and divided by this 1 plus sum of Ci squares. That gives us the first n coordinates. The last one is given by 1 minus sigma Ci square by 1 plus sigma Ci square. Now then we have to apply phi on this. To apply phi on a bunch of numbers, all we have to do is divide the whole thing by 1 minus an plus 1. So we need this quantity 1 minus sigma Ci square by 1 plus sigma Ci square, which is the an plus 1 in this case. Now if you take a look at this simple algebra, will show you that this is actually twice sigma Ci square by 1 plus sigma Ci square. Now if I divide the first n of these coordinates by 1 plus an plus 1, which is what we need to do to find out the result of phi acting on these n numbers, the result is very simple. The 2 cancels out. In fact, the 1 plus sigma Ci square in the denominator also cancels out. And you end up with a division of the coordinates C1, C2, Cn by simply the sum of all the Ci squares. Notice that because we have removed the origin from Rn, and we are only talking about points in that space, the sum of Ci squares is never 0. So this is a perfectly legitimate calculation. Not only that, it is very easy to figure out that the functions involved here, C1 by sigma Ci square, C2 by sigma Ci square, etc., are smooth functions. They are differentiable as many times as you want on Rn without the origin. Hence, phi composite chi inverse is an example of a C infinity function, a function which can be differentiated as many times as you want. And of course, all its derivatives are continuous. A very similar calculation can be done as far as the other transition function chi composite phi inverse is concerned. That of course takes phi of U intersection V, the same set Rn without the origin, to chi of U intersection V. And here, if you look at it in 2 steps, and then calculate the whole thing, it's easy to see that if you start with a bunch of numbers b1, b2, bn in phi of u intersection v, and remember, it's a point in this set, so all the bi's cannot be 0. Applying chi-composite phi inverse together gives you this bunch of numbers b1, b2, bn divided by sigma bi squares. So these two maps, phi composite chi inverse and chi composite phi inverse, can be perhaps shortened if you use the vector notation. The first one simply takes the vector c to a new vector c divided by the length of c square, and the inverse of that, chi composite phi inverse, takes a vector b to b vector by mod of b square. Obviously this means that both of these maps are one and the same map, and the map happens to be self-inverse. Indeed, this should be a very familiar map, especially to physics students, because this is what you do when you invert a point about a sphere of radius 1. If you have ever carried out a method of images solution of the problem of a potential due to a point charge in front of a sphere, you have actually seen this particular map. The important point here, as far as we are concerned, is that the transition maps, phi composite chi inverse and chi composite phi inverse, are both smooth functions. They are differentiable as many times as you want. And so these two charts, the two stereographic projections, are actually C infinity compatible. An immediate consequence of this is the following. If you have a function f from Sn, the n-dimensional sphere, to the real line, and if this function is ck according to the chart phi, the chart that we get from stereographic projection from the North Pole, at any point P, then it is automatically ck according to chi, the other stereographic projection from the South Pole, at the same point. Notice that we are considering P to be any point on the sphere other than the North and the South Poles. For the second example of compatibility of charts, we will revisit another old friend. The set SL2R, the group of all 2x2 matrices with unit determinant. Of course, real matrices. That's the R in SL2R. Once again, we have already found out two charts whose domains cover the entire set SL2R in a previous lecture. One of these were a chart where you consider U to be the set of all SL2R matrices A, B, C, D with the condition that A is not equal to 0. And what the chart does is that it maps using phi a matrix A, B, C, D to the triplet A, B, C. Since A is not 0, you can figure out what D is from the condition that all these matrices must obey. Namely, the determinant is 1 and therefore AD minus BC equals 1. Now, phi of u here is actually not all of R cube, not all of three-dimensional space. You actually have to omit the A equal to 0 or the first component equal to 0 from this. That is, you are going to only get triplets A, B, C where A is not 0. Phi inverse takes a triplet alpha, beta, gamma, let's say, and recovers the matrix alpha, beta, gamma. These are of course the same as these numbers, with the fourth entry of the matrix being given by 1 plus beta, gamma by alpha. Note that one condition on the triplet alpha, beta, gamma is that alpha is not 0, and only then will this point be in phi of u. And therefore, this particular calculation that we have done here is a perfectly legitimate 1 to 2. So this was one of the two charts. This chart does not cover all of SL2R simply because matrices in SL2R for which A is 0 are not covered by this chart. The other chart that we are going to talk about, in fact one we have already figured out before, consists of a domain V and a map chi. V is the domain of all SL2R matrices in which B is not equal to 0. Since A and B cannot both be 0 together in an SL2R matrix, after all SL2R matrices are invertible matrices, if A and B were both 0, the top row of this 2 by 2 matrix would have vanished, making the determinant 0. And therefore, as we have said, A and B cannot be 0 together. So in this case, you can easily see that U and V together account for the entire set SL2R. That is, U union V is SL2R. Now, the map chi in this case exploits the fact that if you do not know C, but B is not 0, and you know the other three numbers, you can figure out C from that. Chi essentially takes the matrix A, B, C, D and returns the triplet A, B, D. C is something we can recover back for the inverse map, chi inverse, from the knowledge of A, B and D. Here, chi of U is simply the set of all triplets in which the middle component, the B component so to speak, is not 0. So, those are the triplets which have been deleted from here. And what about chi inverse? Here, if you give me a triplet of numbers alpha, beta and gamma, they will give me the A, B and D elements of the matrix as alpha, beta and gamma respectively. And the so-called C element, this one, will have to be figured out using the fact the determinant of the matrix is 1, and that immediately gives you alpha gamma minus 1 by beta as this element. Once again, since the middle element of the triplet cannot be 0 here, beta is not 0, so this is a perfectly legitimate calculation to do. So now we have two charts, and the intersection, U intersection V, is simply the set of all matrices A, B, C, D for which both A and B are non-zero. Let us now examine what form phi of U intersection V and chi of U intersection V takes. Once again, its simplicity itself, you can easily figure out that if you apply phi on U intersection V, you are going to get the numbers A, B and C, or the three numbers, if you call them alpha, beta and gamma. The condition will be that alpha and beta will not vanish. It's easy to see that exactly the same will be the case for chi of U intersection V. What about the transition functions? Phi composite chi inverse, well, let's start with alpha, beta, gamma, a triplet, and do this in stages. If I apply chi inverse, then alpha, beta, gamma obviously becomes this matrix, alpha, beta and gamma sitting here, and alpha, gamma minus 1 by beta sitting in the C position. Phi will return to me A, B, C, which means it will give you alpha, beta, alpha, gamma minus 1 by beta. What about chi composite phi inverse? Here, alpha, beta, gamma, if you apply phi inverse on that, gives you alpha, beta and gamma for A, B and C respectively of the matrix A, B, C, D. And the dth element, the last element left, can be figured out from 1 plus beta gamma by alpha. And now if you apply chi on this, it will give you these three numbers. This one, and this one. So you will get alpha, beta, 1 plus beta gamma by alpha. Now it's easy to see that both of these functions, phi composite chi inverse and chi composite phi inverse, are genuine proper functions, alpha and beta not being 0 in our domain phi of U intersection V or chi of U intersection V, assures us that these calculations are legitimate, and since these calculations involve simply multiplications, addition by 1 and division by a non-zero number, it's easy to see that they are differentiable as many times as you want. So phi composite chi inverse and chi composite phi inverse are C infinity functions, and these two charts on SL2R hence are C infinity compatible. Now, one of the common features of the last two examples have been that the two charts that we have talked about in both of these cases have been enough, in the sense that their domains together cover the entire set. However, in the case of other sets, or even in the case of these same sets, if you use different charts, it's possible that you would need more than two charts to cover the entire set. Now, in this case, if you have multiple charts covering the same set, perhaps more than two, you would still be able to talk about compatibility of all these charts together. Of course, compatibility as we have defined as yet is actually a matter between two charts. And so, basically when we say a bunch of charts are compatible to each other, what we really mean is that they are pairwise compatible. In other words, if you have a collection of charts U1, Phi1, U2, Phi2, etc., then they're all compatible to each other if for every pair I, j, the charts Ui, Phi I and Uj, Phi j are CK compatible. And such a set of CK compatible charts together can help us map out entire M, or in a more technical language, form a CK subatlas on M if the union of all the domains U1 union, U2 union, U3 union, ... is actually all of M. In other words, these charts together form a way of assigning coordinates to every point on the set M, and wherever two such charts overlap, these transition functions are actually CK, and therefore you have a way of talking about up to kth order differentiability on the entire set M. Let us now take a look at a few examples of subatlases. Why exactly do we call this a subatlas and not an atlas will be clear in a while. But the very first example that we will take a look at is the first example of a chart that we talked about in our very second lecture. This is a case where the set M is Rn, and for U, Phi, we have taken Rn itself and the identity map. Now in this case, this one single chart covers all of the manifold, all of the set, and therefore this alone will give you a subatlas with one chart and one chart only. Here, of course, compatibility is a bit of a trivial statement, simply because there is only one chart and it definitely is compatible with itself. Continuing along the same lines, we have also talked about putting charts on the sets mat2R of 2x2 real valued matrices and GL2R, the group of 2x2 real valued invertible matrices. And we have seen that there too we could make a chart which actually covers the entire set, and therefore you could have subatlases for these two sets which consist of a single chart alone. Going further, we have just seen that Sn, the n-dimensional sphere, and SL2R are two sets specifically for which a single chart did not work, but we did have two charts, the union of whose domains covered the entire set. So these two charts, because they are compatible with each other in both cases, together form a subatlas of these two sets. Now there of course could be, and usually are, more charts than that make up a subatlas. Once you have a subatlas, you have enough material in your hands to cover the entire set, and therefore you are in a position to talk about differentiability of any function all over the set. But if you actually are using more charts than that, and sometimes that may be convenient, you have to worry about compatibility of these charts as well. And this brings us to the notion of what is called an atlas. An atlas is in a way slightly impractical in the sense that for an atlas, you are going to talk about the collection of all charts that are CK compatible with every chart of a CK subatlas. This collection of all possible such charts, which are usually infinitely large in number, is called a CK atlas. Now notice that we are demanding that all of these charts that you are introducing here are CK compatible with a given CK subatlas, which means that you have at least enough charge to cover the entire set, and you are adding more and more charge to that. This should make perfect sense to a physicist, because after all, you all know that there are infinitely many different ways in which you can put coordinates on a space. So even in the case of Rn, where a single chart worked, you could very well have infinitely many charts, and in fact sometimes using some other chart than the standard one that you started out with could be more useful. Things like using polar coordinates, for example. So, come to think about it, every time you use a change of coordinates in physics, you have actually used a different chart. Now, it might so happen that these new charts cover the entire space on their own, so they could have formed a subatlas, or it might also happen that they don't. For example, polar coordinates, which we are all used to, do not cover all of a plane in R2. But that does not really detract from the utility of polar coordinates. But the important point here is, because all of these charts that you have in a CK atlas are CK compatible mutually, it does not matter which ones you actually use, as long as you use enough of these charts taken from an atlas to form a subatlas, that is, to cover the entire set. You are in a position to talk about differentiability of functions. Not only that, if you were to replace a few of those charts by other charts which are CK compatible, that is, other charts which are in the same atlas, the conclusions you draw about differentiability of functions will not change. And this is what we mean by providing a differential structure on a set. Specifying a CK atlas on a set M gives a differential structure. This is a setting which allows us to do calculus on M, and in a way it allows you to do that independent of the particular charts you are using. Of course, to draw a particular conclusion, you may have to refer to a chart, but you are assured by the CK compatibility of all the charts in your atlas that if you were to use other coordinate systems, other charts, you would still end up with the same basic conclusion. So your charts may change, the numbers you use to describe points may change. In fact, the proxy functions f composite phi inverse, whose differentiability you are going to look at, that may change. But the conclusions which really matter, is the function differentiable r times? That will not change as long as r is less than or equal to k. Now, in today's lecture, we have been careful and talked about CK compatibility only. However, in most situations, at least most situations that are useful in physics, we are not going to bother about CK compatibility. We are actually going to talk about C infinity compatibility. That would give us a smooth differential structure. And when we talk about differential structure, we are going to usually mean that unless otherwise stated. There is, however, another important case which works in the opposite direction. If k is 0, what you have is that all the transition functions are guaranteed to be continuous, not guaranteed to be differentiable. If that is the case, you can talk about continuity of functions on this set using these coordinate charts, but you cannot go any further. In that case, you call your set a topological manifold. If k is 1 or more, the structure you have, the set M along with a CK atlas, would be called a differentiable manifold. And as I've said, usually we will be dealing with a special case of differentiable manifolds, smooth manifolds. In fact, when we say differentiable manifolds in the future, we would usually just mean smooth manifolds, C infinity manifolds. Now, if you were to study a mathematics text and look up the definition of a differentiable manifold, you will see that typically there are some conditions put on the set M before you begin to talk about charts, their compatibility, and hence atlases and subatlases. Usually a mathematics text would start with a statement that let M be a second countable Hausdorff topological space, and then proceed. We have not done that here for two reasons. one, we are physicists and we don't really understand things like second countability, etc. that well. Much more importantly, it can be shown that even if you did not start with a topological structure on your set, the atlas itself provides you with a topological structure which is guaranteed to be second countable and Hausdorff. So in a sense, the typical mathematics books opening is a bit of an overkill. We don't really need that. Before I wind up today's lecture, let me just point out one thing. That's more about terminology. We have defined a CK subatlas as a bunch of mutually CK compatible charts which cover your entire set. And a CK atlas as something which you get when you add to a CK subatlas all possible charts which are CK compatible to that. In some mathematical texts, the terminology is slightly different. There, what we are calling a subatlas is called an atlas, and what we are calling an atlas is called a maximal atlas. So, if you are reading a text, please make sure what exact terminology is being used here to ensure that you do not get confused. Now, as we have said, the whole point of having a differential structure is to be able to do calculus. We have already seen an example of that. We have been able to check whether a function f from M to R is differentiable or not using a structure like this. Of course, you could think of more general situations where, for example, you are talking of functions f which carry you from one differentiable manifold M to another differentiable manifold N. And it's easy to generalize the notion of differentiability from the special case that we have talked about, functions from M to R, to these cases. And there is a lot more to discuss about functions, curves, tangents, vectors, tensors, and so on. But all these will have to wait for later lectures. Let me wind up today's lecture here. Bye, till we meet again.